Okay, so we have the time is to start. So let's start today's seminar. Hello everyone, welcome to the Energy Visions seminar series. So today is the number 9 series, and today's topic is about planning urban energy systems adapting to extreme weather. Will be presented by Dr. Rui Jing, and I'm Rui Yao from X Development LLC, and I will be hosting today's meeting. So a little bit about today's speaker. Dr. Rui Jing is an associate professor in Xiamen University. Before joining Xiamen University, he was a postdoc in Cardiff University. His research focuses on multi-energy system, urban energy planning, climate resilient energy systems, and energy-related nexus research. He is now a member of Advances in Applied Energy Young Editorial Board, and he has co-authored 50 peer-reviewed publications. And today's seminar topic is planning urban energy systems adapting to extreme weather. This related research has been published in the Advances in Applied Energy Journal, and you are welcome to follow this paper too. So now let's welcome Dr. Rui Jing for his presentation.
Okay, thank you. Can you hear me?
Yeah.
Okay. Could you please stop sharing so I can start sharing? Okay. Can you see my screen now?
Yeah, I can see it.
Okay. Okay, let's start. Welcome all the friends. Thank you for joining this session. Today's topic is about planning urban energy systems adapting to extreme weather. So this part of research is mainly done when I was in Cardiff University and the Chinese Academy of Science. So here is today's table of contents. First, I would like to introduce some research background and then discuss the methods we proposed and explain it by case study and have some summary and the Q&A session. So first of all is the background. In the background session, we try to explain 3 questions. First of all is why it is important to understand extreme weather. And the next question is about the typical type of extreme weather resilient research. And the third question is the status of resilient urban energy design and planning research. So as we know that climate change and global warming have induced more intense and more frequent extreme weather, such as the wildfire, the ice melting, the flooding, the drought, the typhoon or hurricanes. So as shown here, climate change can induce different abnormal events, which can be categorized based on the time horizon. So such as the instant weather, abnormal weather, the short-term climate events, and seasonal to annual events, annual to decade, and decade to century events. And here in this study, we mainly focus on the extreme weather at this stage, which means it is at the hourly to daily time horizon. And here is a map showing that the selected extreme weather in 2020 such as the wildfire in America, the hurricanes, and the global record-breaking high temperature, and also the drought in Australia, and etc. And this is inform us that we need to understand more and plan the extreme weather resilient urban energy system, as more weather-related renewable energy are now in our energy system. So if we do not have sufficient knowledge to this event, the system or city operator can only hope that next extreme weather will not trigger a sudden blackout. So here, we consider two types of extreme weather. One, it is called the green rhino, such as the solar and wind fluctuation. And this type of abnormal event that the decision maker already aware of it, and it is relatively predictable. So people also call it high probability but low impact events. And recent research already consider it quite well. Another type of abnormal events, it is called the black swan event, and also the extreme weather event, such as the typhoon or heat waves. So decision maker usually not understand it well, and it is relatively difficult to predict or prepare for it. So people also call it lower probability but high impact events. And it is relatively few research to address it, but recently it's quite a hot topic. So we mainly focus on this type of events in this study. And here is a basic concept of the system resilience. We may already know the basic concepts of resilience, that resilience usually includes 4 stages: before, happening, after, and even the adapt evolve stage. And at the before stage, we usually perform the plan and prepare research for it. And when the extreme weather happens, the system will absorb, react, and recover from the events. And since we're dealing with the planning research, so the system design can be changed based on the event. So the system can be even adapt or evolve based on the events. And also the resilience have 4 attributes. The first one is diversity. And it's quite easy to understand that a system with higher diversity is usually more resilient. And of course, a system with higher adaptability and flexibility is more resilient. But we need to know that there's no free lunch here, which means that usually a resilient system will require higher cost, such as spend more cost on the backup power. So based on the concept of resilience and extreme weather, here we use a Boti diagram to highlight 5 kinds of extreme weather related energy system research, which is the planning stage, design, dispatch, restoration, and evaluation. So for the planning research, we mainly focus on the expansion, design, and operation optimization research. And the feature of it is the investment can happens per 5 years or per 1 year or per 3 years. And we need to optimize the investment decisions. And we also consider the operation decisions by simulating multiple typical days and in hourly resolution. And the objective function is usually to minimize the annual investment and the operation cost. That is the planning research. As for the design research, it focuses on the design and operation problem. And the investment is usually at the beginning of the project horizon. And it also considers multi-typical days and the hourly operation. And the objective function is usually to minimize the capital and the operational cost. So the slight difference between the design research and planning research is on the investment stage. So for design stage is usually only optimize the investment at the planning stage, at the beginning. And the planning stage, the system design may involve during the entire time horizon. As for the dispatch research, it focuses on the frequency and voltage protection, and it usually simulates one typical day, and it consider even finer resolution, such as the operation at minutes resolution. And the objective is usually to maximize the reliability. And the next type of research is the restoration. It focuses on the system reconfiguration and the restart from the black status. And it also simulates like one typical day, and it considers the operation and minutes resolution. And the objective is usually to minimize the recovery time. And the last kind of research is the evaluation research. So as we know that to assess the resilience, only one index may not be enough. So it is important to develop an index system. And based on the index system, we usually need to consider the multi-criteria evaluation and also the optimization-based evaluation. So in this research, we only focus on the planning problem here. So we normally use a model to help better understand the urban energy planning. And a typical urban energy planning model usually have three parts: the inputs, the model, and the outputs. In the inputs, we usually need to collect a lot of data, such as the demand data, the resource availability data, and also the technical, economical, and emission data. And we usually have a technology database. And then is to develop the model. The model usually have two elements. One is the objective function, another is the model constraints, a series of model constraints. And then to build the model, and we usually feed the model to an optimization engine and then get the optimal results from the optimization engine or solvers. And then we can get the outputs. The outputs usually consider the annual energy portfolio, the dispatch strategy, the cost, the emission, and the dispatch is usually at the hourly resolution, and the energy portfolio can at per 1 year or per 3 or 5 years resolution. And here is a typical temporal setup of urban energy planning model. And generally it covers multi-year horizon, such as 20 years here. And the horizon is further divided into seasons, days, scenarios, and eventually at the hourly resolution. The investment decision is made at the annual level, and the dispatch decision is made at the hourly resolution. And as we know that renewable and demand profiles are always fluctuating, so we usually use clustering methods to generate most representative scenarios. But for extreme weather events, it is quite easily to be ignored, as it's very low probability and it's high uncertain. So how could we capture extreme weather events in the urban energy system planning? Here are two very good and representative research published in high impact journals. The first one is multi-energy design research considering fluctuating solar and wind. The highlight of it is it raised the importance issue of the low probability, high impact, and the high probability, low impact issue of extreme weather, and it performed a 30 cities case study. The model it uses is stochastic and a robust mixed model. And we can further perform research based on it. The first part is it not consider the disruptive events, but only the low probability event. And also it used the identical temporal resolution and horizon for both extreme weather and the conventional days. But as we know that extreme weather may fluctuate at final resolution. Another good research is electricity network planning research considering the hurricane. And the highlight of it is it embedded the line failure probability into the model. And the model is a typical stochastic model. And the limitation of using a stochastic model is that the future probability is somehow uncertain to predict. And another problem is that it also uses the identical temporal setup for both extreme weather and the conventional days. So these two work and some other works are very inspiring, and they are a solid foundation for our research. So based on their research, we also try to develop models to consider the extreme weather in urban energy planning. And we address this topic from two aspects. One is from the objective function, another is from the model constraints. So first, we try to formulate an objective function to capture the resilience problem. And we built a city-level optimization model. It is a bottom-up model. It considers the hourly dispatch, 20-year planning horizon, and we use the diversity index to assess the resilience, and also compare to the cost objective, emission objective, to assess the trade-off between the system design, considering three different objectives, which is also called balancing the energy trilemma. So other than the emission and the cost, we introduce the diversity index to represent the resilience. And the logic behind is that don't put all your eggs in one basket. So we try to find the most appropriate diversity index, but we can only find the HHI, which is the simplest one, but it is also a non-linear one. So it made the problem, the model, very difficult to solve. So we further develop initial value assignment heuristic, try to speed up the solving process of this nonlinear multi-objective optimization problem. And the basic concept of this heuristic is that we use the optimal results from one solution as the starting point to solve the next point. But it is noteworthy that even though the speed could be partially speed up, but I have to say it's not a good idea to build a nonlinear model for this scale of problem. So we try to avoid the nonlinear models in the further research. We then use a case study to show the the significant trade-off between different objectives. As we can see that the diversity optimal solution, the cost optimal solution, and the emission optimal solution here, and the extra 3.9% cost can achieve a diversity optimal solution compared to the cost optimal. And we also use cost optimal as a benchmark. Then the emission optimal will require extra 27% cost. Then we further try to build models to capture extreme weather. And firstly, we built a typical stochastic model for that. So in a typical stochastic planning model, in each year, we will build a scenario tree to capture the difference of seasons, different days, and regular scenario and the typhoon scenario as a benchmark. But it's quite challenging to quantify the probability of each scenario, but it is the key to build a stochastic planning model. So for the typhoon scenarios here, we have to use the historical weather data, but we do not consider the future change of the weather. So as you can see that for each year, there's a scenario tree, and when the scenario number goes up, the entire model will become super heavy, and the solving time it could be quite long and even make an untraceable or unsolvable model. So based on that, we further propose the original two-layer modeling framework, and we try to avoid a too complex model. So we divided the entire problem into 2 stages. The upper layer is a conventional urban energy optimization model, and it only considers the conventional days scenarios only, and it optimizes the dispatch and the design decisions. And then we further feed the design decision into the lower layer simulation, extreme weather simulation model. If the upper layer optimized design decisions can pass the simulation, which is good, we can directly get the solution for the when the extreme weather happens. But if there's no solution exist, then we further offer 2 heuristics to inform the upper layer model to re-optimize the design, and then through iteration to ensure that all the designs at each year can pass the extreme weather simulation and get results. That's the basic logic of the 2-layer model. And here we introduced the extreme weather simulation. And this model is essentially an economical dispatch model with specific constraints on both supply and demand sides before, during, and after extreme weather. And there are 5 steps to construct such a simulation model. The first step is to determine the simulation horizon, and the temporal resolution for extreme weather depends on the characters of that extreme weather. And then step 2 is to set constraints on the supply availability during the extreme weather. For example, in the typhoon days, the wind turbine may have to stop. And step 3 is to determine the demand to be met during the extreme weather. So the demand may be dropped during the extreme weather days. And in step 4, it could set constraints on the supply availability during the recovery stage. So some technology may require longer times to recover or partially recover when the extreme weather pass. So the last step is to put above 4 steps constraint and settings into the model and run the model. And as we mentioned, if there's no solution exists, we further offer 2 heuristics. One is called the storage prior, which means that when there's no solution, we can increase the storage capacity first. And considering the cost, we tend to increase the pump hydro energy storage first and then the battery, and at last expand the supply capacity of supply side. And another heuristic is the supply prior, which means that if there's no solution exist, we tend to expand the supply capacity first, such as the gas power capacity first, and then install the pump hydro storage, and at last install the battery. And the advantage of such a 2-layer framework is the high flexibility, as it avoids a too complex upper layer optimization model, and then it allows a 2-layer framework and the lower layer simulation model to capture the extreme weather. So let the upper layer only consider the conventional scenario. And since we split it to 2 layers, so the lower layer is quite flexible, as its horizon and the resolution are not limited to the upper layer model. So like in this case, it can consider not typical days, it can consider 4 typical days. And the resolution can be hours or can be minutes, and it's not limited to the upper layer model. And at last, the iteration is also flexible. We can choose annually iteration, or per 3 years or per 5 years are both okay, depends on the needs. So we also use the case study in Xiamen as a case study because it located in the southeast coast of China, and it has typhoon occasionally. So there are some basic information for planning Xiamen's energy system, such as there's no more coal power plants due to the emission control strategy, and the local area have sufficient natural gas supply, and it has sufficient import power supply from the Fujian province utility grid. And it also has the potential to develop the local pump hydro energy storage. So in this case study, we consider 3 scenarios. The first scenario is the benchmark, which means we don't consider the extreme weather, so there's no extra cost. And in scenario 2, we consider the extreme weather by the storage prior heuristic, and the result shows that 2.8% extra cost is needed. And for scenario 3, we apply the supply prior heuristic, and it will cost extra 5.4% to fulfill the energy demand when the extreme weather happens. So here is the design and the capacity expansion plans, the optimal results. And here is the benchmark when the extreme weather is not considered. And when we consider the extreme weather by both 2 heuristic, we can see that larger capacities, total capacities are needed in general to ensure the energy demand to be fulfilled during the extreme weather. And in the storage prior, as you can see that we tend to install the PHES first, and when its developing potential is fully developed, and then we choose to install batteries. And as for the supply prior strategy, so the capacity expansion plan tend to install more capacity of natural gas power to ensure the energy supply. And here is the system dispatch before, during, and after extreme weather when we adopt the supply prior heuristics. And here we intentionally model 2 days before the event happening to let sufficient time for all the technologies to act. And as you can see that in the supplier prior heuristics scenario, since there's no storage, so the renewable power has to be curtailed. And when the extreme weather happens, the demand will drop to a lower level. For example, we consider only the essential demand here. And the gas power is flexible to ensure the energy supply. And when the storage prior heuristic is adopted, we can see that since the storage exists, it helps to better use of renewables during the daytime. And when the extreme weather happens, the storage can also help to cover the peak, and the coal and the gas power can cover the basic demand. And we also consider a recovery day. And in this case, we just assume all the technologies can immediately recover after the event, but it can be altered based on the specific demands. So let's basically the case study and the findings from our methods. And since the resilience is quite an open question, and it becomes increasingly important as climate change indeed bring more intense and frequent extreme weather, such as the heavy rain for 3 weeks that is happening in my location, Xiamen, at the moment. And the freezing cold and the snow for the first time in Xiamen, such a warm city, at the beginning of this year. So resilience is indeed an interesting topic and deserves more investigations. So here I don't make a conclusion, and instead I'd like to share some potential future research questions. And the first question is about the energy network, which means that we can consider the multi-node energy network and the multi-energy system to investigate the complementarity between different energy sectors and the different zones complementarity, and also assess the possible damage of part of the network. And the next question is about the index for resilience. As I mentioned, maybe it is not easy to use only one index to quantify the resilience, and we may need to construct an index system to quantify the resilience. And when we develop the index, and we need to consider how to merge it into the models, either as objective or as constraints. And the third question is about the prediction of the probability of extreme weather. And as we know, it is quite challenging to accurately predict the probability of future long-term extreme weather, especially at the final and accurate resolution that the energy system model usually need. And the last question is the extension. As you can see that in our study, I only perform one case study and consider only one extreme weather. And the future research can consider that one city with various individual extreme weather, and also it can consider the possibly the sequential or mix of extreme weather to assess their impacts on the urban energy system. So those 4 potential questions are what I think is deserve more investigations. So that is basically the end of my sharing today. And here is the link to our latest paper, and with more details about the methods we propose. And here is the contact of me. And thank you for all the supports from the co-authors, the institutions, and also the journal, the platform. And thank you all you guys for today's listening. Thank you.
Okay, thank you very much, Dr. Jing, for the great presentation. That was very informative, and I learned a lot from that. So next we'll have about 20 minutes of a question and answer session. So if for all audiences, if you have any questions to ask and want to discuss with Dr. Jing, please feel free to unmute and then ask your questions. Okay, so here is one question popping up from the audience. So can you explain how you decide the EWE scenarios, especially EWE under climate change?
How I decide extreme weather scenarios? Maybe use this. Can you see the slides now?
Yeah, I can see it for myself.
Okay.
Yeah. Mm-hmm.
So I have to say there's no definition for extreme weather, considering the considering the climate change are evolving. So usually we consider such as the events here, like wildfire, the drought, the flooding, and the hurricane or typhoon, depends on the time resolution of it. So like here, it's we consider the hourly to daily resolution events. We consider them as the extreme weather. And the question, sorry, let's go back to it. Oh, okay, I see the question.
Yeah, the question was posted on the chat. You can see that, yeah.
I think to decide the scenario. Decide the scenario. So first is we need to decide which kind of extreme weather we need to address, which is what I explained before. And also the next question is to quantify the probability of it. And at the moment, I use the historical data. and I haven't considered the future climate change induced the changes in probability, but that's a quite interesting question that I mentioned and further deserve investigation. So basically 2 steps. One is determine which extreme weather you want to assess, and the next one is to measure its probability. That's my answer. Thank you.
Okay, thank you. And here's another the question from audience. For real implementations, designers in industries usually have relatively ample funds than academic projects to support heavy computation and find the numerical optimization solution. In this case, what is the role of simplifying the method, like what you have used in the real implementation? Yeah, I think that's more like kind of if more computation resources available, if we have to use the simplifications.
Yeah, that's one. Yeah, that's one inspiring point for me to perform this research. Yeah, I try to avoid too complex problem in one model, because if it's require heavy computation, it's easily to get uncontrolled of your model. So I try to split up problem into 2 layers to ensure that I can control every part of it. And as for the real implementation, I'm sorry, at the moment, I don't have any real implementation. But the case study that I used for Xiamen, the data are real. And I compare the simulation data with the real world data, and it makes sense. So the case study itself makes sense, but I don't have a real implementation at the moment. That's my answer. Thank you.
Yeah, actually, I have a little bit to follow up. So I see that your two-stage or two level framework. Mm-hmm. The upper level is for optimization, and the lower level is for simulation. And because I have worked on some resilience modeling and simulation work, so there are actually a lot of resilience modeling and simulation existing works and pretty good simulators available. Maybe each of them are focusing more one factor. They are really good at like simulating some details for maybe some scenarios. So is your framework compatible to these existing simulators? For example, if you want to leverage those existing simulators, can you put into your framework?
To be honest, I didn't compare them. And I think you are raising a very important question. So that I have to compare my model with others. I think what I try to propose here is more about a concept of splitting problem into 2 stages. So, we can, of course, embed it. The very well-developed simulator at the lower stage and combine with another planning model at the upper layer. So it's more about a concept of splitting problems, and yeah, so it's not limited into a specific model at the lower layer.
Yeah. So my understanding is that it provides flexibility for not just not just limited to your modeling, but it can be it can also use other simulation models, right?
Yeah, sure. Yeah.
Okay. Yeah. Thank you. Okay, and other question from the audience. One is, so there are two questions. One is how to quantify energy resilience. And second is that the extreme weather is low probability, high impact. What is the impact on multi-energy system design and operation? And third is a solution to enhance the energy resilience. Yeah. Any thoughts about that?
Oh, these three questions are all very important and fundamental. So for the first one is to quantify the resilience. So as I mentioned, I think maybe one index is not enough. Maybe we need a index system. So like I do here, I use the diversity index, but I found actually it's not a very good one, as it generates a nonlinear problem. So I think like in this case, essentially I converted the unmet demand into the cost by the value of lost load. And I think that would be a quite good one. But to be honest, it is still developing questions. And the general answer is that it's not easy to quantify it, and we need to have an index system. So for the next question is about the extreme weather is low probability, high impact, and what's the impact on multi-energy system design and operation? Yeah, I think you already mentioned the answer, that the impact is both on the supply side, which is increase the capacity, and also the demand side, which may induce some demand increase and some demand drop. And the impact on the design and the operation. And my first impression is that since now the energy system have been heavily penetrated by the weather-related renewables, so in a multi-energy system, and we try to handle the LPHI in events, we may still to have sufficient like solid and supply with safety, such as the gas power supply, and also the storage. Storage can play an important role during the extreme weather, and also the demand side management, such as the demand response, and also like using the electrical vehicle as a mobile storage devices are also important measures. And I think to handle the LPHI in events in a multi-energy system, it will require a whole system model to consider both the supply side and demand side, all the measures together. And it will be a quite interesting optimization problem. That's my answer for the second question. And the last one is any solutions to enhance the energy resilience. I think lots of things we can do, but it really depends on what kinds of events we are facing. For example, the typhoon events could be totally different from the drought events. So I think based on the energy DOE, they have two principles for how to enhance the energy resilience of energy system. One is to invest more on the physical infrastructure, and another one is to change the system operation strategy so as to address the resilience problem. So they offer two like kinds of principles, but in details, we need to address the detailed solution depends on the events we're facing. That's my answer for the third question. Thank you.
Okay, so the next question from the audience is, I think it's more on the validation. So since the accuracy of the forecast will affect the optimal design, how the hazard predictions, such as typhoons, are validated with limited data in real implementation?
Since the accuracy of
yeah, I think
yeah, that's
yeah. Mm-hmm.
Go ahead.
Oh no, I just want to maybe interpret, but seems you have got a question. Yeah. Mm-hmm.
Yeah, that's a good question, and it also goes along with my my showing here that the prediction is quite a challenging problem. That I also have this challenges when I do the research, and so far I think we need to have like more interdisciplinary research that combine the climate and the weather related researchers results with our energy research. And I think in the climate change research field, they already done a lot of very good research to predict the future the future weather data, and in a very long time span, such as to 100 years later, and and when we try to use their data, and we have to consider how it can be combined to our energy system model, and what kind of data that we need in our model. For example, I think the time resolution is always a big problem. Like in the planning research, that we normally require at least hourly resolution data. And in the dispatch research, we may further require seconds to minutes data. But that kind of resolution, maybe it's quite challenging for the climate research. So I think a more discussion between the energy research and the weather research is very important to handle the problem. And that's the basic idea of my answer for this question.
Okay, thank you. Okay, yeah, just a point. Okay, so also from audience HC says one, I think we currently have one, but waiting for the other. Let's go to the one first. So your extreme weather, your two-level optimization framework, as we know, increasing generation capacity and increasing storage. The two technologies should cooperate to get a better optimization result. How do you think about this?
Yeah, that's also a very good question. How to say that? When we use when I try to tune in my model, I do consider this question, and based on my experience, when I try to to test my model, and I found that the key factors to determine whether increase generation capacity or increasing the storage is essentially the cost. So if one technology is not limited by its physical implementation potentials, it will be selected at a maximum level until its developing potential by the model. So when I tune in the model, I found that if the pump hydro energy storage is still have availability, then the model will constantly increase its capacity other than increase the generation capacity when I choose the storage prior heuristic. And I found that the situation you mentioned, that both two capacity increase, is actually not happens in my optimization model, I have to say. Yeah, but I can understand your concerns. Yes, I do think it's a more practical and a more reasonable results that two capacities are cooperate to get a better results. Yes.
A quick follow-up from me, actually. Sorry for interrupting before the second question. So you provide two situations. One is putting the storage before the generation, and one is putting the generation before the storage. So for a like a cooperated situation, do you think it's the result will be somewhere in the middle?
Yeah, I think so. Yes.
Okay. Yeah. So this, do you think this will like provide maybe some, I would say, some boundaries or something of this cooperated case?
Yeah, I should design a third heuristic. Yeah, like somewhere between them.
Yeah. Okay. Thank you. And the second question is in the extreme event simulations, you set a 2 normal day first and 1 extreme day. Have you considered do some extreme scenario sensitivity analysis, such as the 2-day extreme event?
Oh, that's a really good question. And in this case study, I didn't consider 2 days extreme weather event, but as you can see that since I split the problem to 2 layers, so the lower layer problem, lower layer model is quite flexible. You can set how many days you want. That's I try to highlight that the advantage of this kind of concept is more flexible than putting all the things into one model. And also the lower layer models, simulation horizon and the resolution are not limited to the entire planning model. That's why I think my 2-layer framework is good.
Okay, thank you. And also, any other questions? We have 1 minute left. If not, I have a last question. So you on pages 22 and 23, you provided some operation scenarios of 2 supply prior and storage prior heuristics. And I wonder what does the base case look like? Like if there are no actions for these EWE events, what does it look like?
If no EWE, I think you can refer to like this one, the day one, the conventional day without EWE.
I mean, what would the system perform when the day 3, the EWE happens?
You mean here?
Yeah. Because there are no like consideration of right. So
I see. Okay.
Yeah.
So in the when the extreme happens, So I assume when the typhoon happens, so I assume that there's no solar power and no wind power. So only the traditional power such as gas and coal still work, and also the storage if they exist, and also the city become more isolated, so there's no imported power from the wider utility grid as well. So like here, it's only the gas, the coal, and also a little bit biomass.
Okay, I see. All right. Thank you very much. We are out of time. So thank you again for Dr. Jing for the very impressive presentation and the very informative and insightful Q&A session. And also, I appreciate all the audience for attending today's Energy Vision seminar. There will be more seminars coming in this series, and please stay tuned. Okay, so thank you very much for today, and have a good day.
Thank you, Dr. Yao. Thank you all you guys listening.